s plus x0 all over s plus a. Okay. Now, for a standard thing as we're considering f of s, it could be of one of several different types of forms, right? It could have the form of a polynomial. Right? Now, if it's a polynomial, I've got, this is a constant, so that easily fits within it. So I would have on top a polynomial divided by another one. So what you would end up doing is you would do division of polynomials. You'll get some constant that sticks out there, plus the remainder over this. And that constant that sticks out there is just going to be itself a polynomial. And that's would be made up of a whole bunch of things, whatever, b1 times s to the k plus, whatever, b2 times s to the k minus 1, dot, dot, dot. Okay? And that's very trivial to actually solve for, but just creates kind of like a bias. Where are you going to? That's the asymptote location. That just tells you where your thing is converging towards. And then the remaining part that's left over, the constant over this, will tell you your displacement from that asymptote. Realize I can give you a curved asymptote. It's no problem. It's a tracking thing. So if this was, some type of a, curve going like that, I would just be following, and my displacement is just telling me how far off I am from that. Right? This could generate all kinds of fun, complex things that are going on. My point just being you follow it. Now, the most common one you get for this type of a situation is where I've got either a constant up top, it's a very simple polynomial, or I've got something that looks like s plus b. Okay? Those are the two most common ones we will kind of consider. So of this one, the ones we're most going to be concerned with is some constant k or s plus b. Notice there's other things that this could be. This could involve trig functions or exponentials. And so it could look something, all of those we've mentioned look like, something like e to the cs, because we're in the s domain. And remember these right here, when you get this exponential, it's talking about what happening in the time domain. Exponentials here was one of our properties. It's a shift. Right? Remember, it displays left or right, the whole function? Yeah. Right? So you can think of this, when you see this, think delay. Right? It's been shifted to the left or right, it's been delayed, or it's been sped up. It's that idea of being able to shift that leads into the idea of lead-lag control. You're adjusting the lead or the lag, so, these are kind of common things that you're going to see. We just kind of hit every polynomial and all the exponentials as it goes in, which covers your trig functions. We can obviously expand other things in them. So if you understand how these kind of work, then it will make perfect sense how to extend it to those. That's just my own little side note, because pretty much everybody starts and just does k. Right? And once you just do k, and then we just say that covers everything. And it's true, but you don't necessarily know why. So first, what I'm going to do is we've kind of gotten an argument why this covers pretty much everything we're interested in. So I'm going to show that this one just reduces down to this with a minor modification. And these ones were just shifts, so who cares about that? That's trivial. It's the same thing, just a little bit later. So all of this kind of reduces down if I can show that goes to that, with potentially funny-looking asymptotes coming off. All right. So let's assume I've got s plus b over s plus a. That's this case. Now, this right here I can consider as being equal to s plus a minus a plus b all over s plus a. Do we agree? What's the trick I'm using?
Plus 0.
Add nothing. Right? Remember, I told you all the time, math tricks come down to multiply by 1 or add nothing. I added nothing. A minus a. But what I've got now is, I don't know about you, but I hate doing polynomial division. So I don't want to. I just remove the need to do it. I'm going to do polynomial division and get the remainder. I just don't want to do any work. So I just want to do it for free. So I've got s plus a over s plus a. That's equal to 1. And then I'm left with b minus a over s plus a. So this is in the S domain. What's the inverse Laplace transform of that?
Delta.
Right. That's pretty simple, isn't it? Little boom. Okay. So no problems with that as we go through. So I got a spike, a jump, some initial hit to get the whole thing going if you want to consider it. And then this, b minus a, is just a constant. Number minus another number. So I just call that k. So I submit to you, I can therefore very easily describe my whole system now. If I tell you how this works, that one you already know how it works. Fair enough? Just as another side note, you will sometimes see people also do this one, kind of a 1 over s or a k over s type thing as it goes on. That's another fairly common one to stick in there. If you think about what really happens with that one that's going on, 1 over s ends up giving you what type of a function? A step. Right? So you end up, when you do synthetic division, which is how you separate that one up, you'll end up getting a step function and you'll get an exponential, and the exponential is usually negative. So the step function is here, and then you're taking an exponential subtracted off from it. So it's no big deal. If it adds onto it, then you're doing this. So the plus or minus the exponential just tells you, are you coming from the under or the top? Am I decaying down to a bias or powering up to a bias? Right? And then we just call that the asymptotic behavior because the step function lasts forever. To realize pretty much anything else you do will reduce down to the same type of behavior. Now, the reason why I go into that is now all I'm going to worry about is just what everybody else does. What if the top is k? Okay? As we just showed, everything else is that. So if you know how to do that, you're fine. We agree? Mm-hmm. Awesome. So that means this is equal to k over s plus a, however you calculate k out of there. Golden. All right. Now, there's a couple ways we can actually do this. The easiest way is just look it up in the table because we already found this one. Anybody remember we developed all these ones? Anybody remember what that was?
Going back to the time domain time.
Time domain.
K times e to the negative a t.
K e to the minus at. Huh? So that was one we'd already developed several days ago when we made those Laplace transform tables. If you don't have your Laplace transform table, just pull it up on a computer sometime. Print it out, go ahead. They might even have one in the back of the book. It's fairly common as we go. So this is our Laplace transform pair. Now, obviously this right here is a function, is determinant. So what that a is, right, which is right here, is going to determine the behavior of our system. So let's pick a couple important values of a. What do you think is the most critical, kind of the boundary? Because there's different behaviors this can have, right? Like for instance, if a is positive, what does this do?
Decays.
Huh?
Oh, in that case.
If a is positive, it's going to start at what value?
Positive.
Well, it's going to start at k. You just put in t equals 0, right? So it's e to the 0, which is 1, so it just starts at k. So it starts at k, and then how's it going to behave for a greater than 0? Well, it's minus a, so it's going to be a decay. Right? And the minus a will determine how fast it decays. But the fact that it decays, not going to change. So the only thing A at that point is determining, once you know that A is positive, it just determines how fast. What happens if A is a really small positive number?
Okay, really slowly.
All right? Yeah, it's going to decrease really, really, really slow. Because if A is really, really small, right, any practical size value times a really small number is small still. Which means it's e to something really small, which means e to something close to 0. It means it's going to stay close to 1. So if A is very small, you expect to see that same curve, general shape. If you were to zoom out, it would look like this, but it'll be a lot slower than another one. If A is a really big in magnitude,
Drop really quick.
it's going to drop off really fast, but still have that same lovely lasting on forever type of a tail. Make sense? So consequently, if what we had up here was a 1 over s type of thing, so you had a step, what are you going to see? 1 minus this, or let's just say k minus this for the simplicity. Well, that same function, so this is just so you can kind of picture it in your head. Right? If I'm doing k, a constant, minus this, it's going to start at 0, k minus k. It eventually is going to get this function, so if I'm doing k minus this, which is what if I had a 1 over s, right? Then you would expect to see eventually this runs to 0, so your final value will be k. So I'm heading off to k. And in between, it's k minus that. So this flips, and you'd expect to see that. So if you think about it for a second, when you go through your physics courses and whatever, you've probably seen that a whole bunch of time in responsive systems. In reality, it was just taking a look at this going on. We call these the transients. So this is the transient part of your signal that's going on, and then this is your final value. That's where it's asymptotically going to. When you go for engineers, you typically have a period of time when your system's kind of warming up or initially responding to something. We say until the transients die down. We're just saying until this portion gets small enough that it's close enough to there that it's good. And that's usually defined as some percentage. Usually we say 4% or 2% or 1% or whatever amount of noise we'll allow on this signal to where the response is damped off that we can't tell the difference between it and noise. Right? And so the period of time it takes to reach that just tells you what we call the settling time. You know, how long until this value is close enough to the final value. But realize, all you have to do is take a look at that, because these are the transients. Make sense? Is everybody familiar with how to graph quickly? An idea? Right? You pick the starting value, you ask where it's going to, and then you get the shape of what's going in between. Okay? We don't actually, if you notice, I didn't calculate any points in between. But I can tell enough of the behavior because I know the shape. So if I know the start and the finish and the shape, I can give you a pretty good idea about what's going on inside the system. And that's often all we need, because remember, I can program up MATLAB or whatever you want, LabVIEW, whatever makes you happy, to get a really close curve. But how do I know that it's giving me something reasonable? I know the start, I know the end, I know the shape. If it violates that, I'm upset. If it follows that, then I go, okay, it must have been okay. Right? We're very good at getting these things rather quickly as an approximate check, and it's a good system check to what's going on. As that's what you really kind of want. Do we feel comfortable with what the curve looks like? Now let's think about correspondingly, so this is really the one that matters, the transients. Let's think about what that means for this function, the S domain. You've seen what it looks like in the time domain. What does the same thing look like inside of here? Okay? Now, when we're taking a look at the value of A, if A is positive, What we're really concerned with in a function that looks like this is one, this function cannot be calculated. Because I can calculate this for any value of t, can't I? Can I calculate this for any value of s?
No.
So that becomes a significant point. Because remember, when you're trying to understand a function, you want to know the significant points. Where does it start? Where does it end? Does it become uncalculable someplace? Right? Where does it cross 0? Things like these are significant points, and then you just want the shape in between. When you look at this function, you go, uh-oh, I'm dividing by a variable. When I divide by a variable, I can get division by 0. Okay, so that becomes kind of a significant thing to us, division by 0. We have to know where that happens. Where does this happen?
Make s equals -a.
When s equals minus a. Now, what does it look like as you're getting close to s equals minus a? If I were kind of, let's say, here's s. I just put a little x there to mark where it's at. As I'm getting closer and closer to it, what happens to the magnitude of this?
Blows up.
Yeah. If you're looking at this as I'm going down, here's my real part of S line, and this is the magnitude of that. So magnitude of K over S plus A. All right. So if I take a look at that, and this is the real part of S, as I get closer and closer, so let's say this is minus A, I've got 0 here somewhere, which is the real axis. I should probably draw it there. All right. As I get closer and closer to it, it does that, doesn't it? If we're considering just the magnitude, on either side it does that, doesn't it? What does that kind of look like? It looks like a pole, right? Big pole sticking. I mean, you got everything flat. Imagine your function is kind of like a tarp. You just stuck a pole up through it, whatever, your blankets, a tent, whatever makes you happy for that. But it looks like a pole sticking underneath the sheet, doesn't it? So we call these things poles. I mean, and therefore this is what governs the behavior. If you know where that pole occurs, you know what minus A is, which means you know the behavior. If minus A gets really close to 0, what happens?
Awesome.
It's really slow. This one will never oscillate.
If you get to, yeah.
Right? So as I get closer and closer for this one, I get closer and closer to straight flat. Right? It's getting slower and slower to damp. So this way it damps slow. I should actually just make sure we put, this is the actual axis. This is real part of S equals 0. Right? All right, so as this pole moves in towards here, it gets slower and slower in damping. As it moves out here, magnitude of A is getting bigger, so damping becomes faster. That's how fast does it get rid of the transients. So the further you see that pole pushed away from the axis, the faster it's going to damp off. The faster it goes away. Make sense? What happens if I actually have the pole right on the axis?
It'll stay constant.
Well, if that's A is on the axis, A is equal to 0. Right? So that's K over S. What's the inverse of K over S?
Okay.
It's a step function, right? So it's constant the whole way. You could also think of it in this terms, right? If I'm just looking at the transient and A goes to 0,
Okay.
just goes to 1 here, so it just goes to K. So notice you can actually think of that stunt function as directly falling out from our exponentials. Exponentials generated those too. Its step function is just this and A equals 0. Right? But it's kind of a fun extension as it goes on. Now, therefore, when I hit here, it's going to stick around forever. What happens when that A becomes negative?
It grows.
Right? When A becomes negative, minus A is positive, which means this becomes e to some positive number times t. So it's going to still start at k, but now it grows exponentially. Does that make sense? And the rate at which it grows depends on how big is A. What if A is really close to 0? It's going to be really slow. So it'll be, if A is small in magnitude, it's going to do something like that, but it will grow. If you zoom out far enough, it'll look just like that one did. What if A is really large in magnitude? You know, whack, right? It's going to go up quickly. Make sense? All right. What does that mean? So we saw as this goes here, move it this way, it damps quicker. Move it this way, it damps slower. You hit here, it doesn't damp at all. It sticks around forever. Once you go past this line, it starts to grow. If you get closer here, it grows slower. You go this way, it grows faster. Huh? So in between damping slow and growing slow, right at that where they meet point is doesn't grow or damp, it just stays constant, never goes away. So you can now actually look at any single pole right on the axis, and you can immediately tell what the system does. You just look where it's located and you know what the behavior is. That pole will generate one of these curves. It has to. So realize you just analyzed the entire real line, right, of the S-plane. And you can just stare at it and you can tell me exactly what the function does. Now, which of these would you consider better behavior? Which one do we want?
Decay.
We want decay. Why do we want decay?
Because it won't blow up and destroy the system.
Yeah, think about this in a practical system. Think of this as your system response. Any one of these ones that grows. In order for your system to do this, this is saying it's either moving faster and faster or going some location that's faster or faster, and exponentially so. How do you supply that? In order for it to do that, you've got to give it energy, right? So as you keep moving out here, how much energy is it requiring? More and more and more and more, right?
Does it depend on A?
You know, well, it depends on A and time.
Yeah.
A small, A that's still going to cause growth over enough time is eventually kind of so. At a certain point, can you supply that? No. Right? So is that a good behavior? Something that's going to gobble up every piece of energy in the universe and then cause everything to go away? Is that a behavior you want out of your system? Yeah, long before that happens, you're going to blow a component up, okay? Because they're just not going to be able to dissipate the heat associated with that.
Multiplier.
Okay? But, if you see something move too suddenly and it blows a fuse or whatever, right, you grew too fast. It couldn't handle that growth. So that behavior should be in some sense reasonable to you. I don't want this. Right? I want to have something affect, and then I want to stop. If it does that, is that good behavior? Yeah, I mean, I give it, that's a finite amount of energy required to accomplish this. That's doable. It gets someplace I want, right? And then all these transients that I didn't want to deal with anyway go away, and it goes to some known stable position. If you want to go somewhere else, push it again. Okay? So that's reasonable behavior as it goes. We actually really like that. How about this kind of marginally stable thing?
Would be nice.
Right? It's livable, isn't it? It's not great, is it?
No.
You go a little bit too far past that point, and it blows up in your face. Plus, think about it. I mean, this is lasting on forever like that. That's kind of like I turn on the light switch and I never turn it off. Do you want to pay for that?
No.
Right? I'm still requiring an unbounded amount of energy to make this thing go. So it's not bad like that is, which keeps requiring more and more, but it's still not good. So we call this, when you go to the left side over here, we call that stable. Right? You do it, it's not going to go crazy. It'll kind of damp down and eventually come to a stop. That's stable behavior. All right, over here we call that unstable. It just grows without bound. Right in between, we call marginally stable. All right, it's stable but on the margins. You go a little too far to the right, boom, it's going to blow up in your face. So just remember, you always want your poles in
The left side.
the left half plane. If the poles are in the left half plane, it's stable. So now you can just look at a plot of your S domain and tell stable, not stable. Anything on the right-hand side that are X's, it's out of there. Right? It is unstable, and we will have to do something to move those poles over to the left half of the plane. So this is the big thing that goes on with control is, if you want me to get someplace faster, it means the transients have to go away quicker. So what are you going to want me to do?
Decay faster.
You don't want me to shove the poles more that way. So if you have a particular make it go away response, inside the S domain, I just say, hey look, in order to achieve that, I need that to be, you know, an A value that's at least some, you know, value of, say, A sub 0, some minimum amount. So this is the stable area. I don't want to go in here, that's too slow. You just got to move all your poles left of that line that covers your minimum time. So if I see them all and there's a boundary zone before that axis, I know they're going to all, no matter which one you excite, no matter which one of those poles is dominating the response, I know it will finish by a certain time covered by that line. It's a minimum requirement. Right? Does it make sense? Now, ultimately then, it would be wonderful to have absolutely everything in the universe way over here on the left-hand side, wouldn't it?
No.
Yeah, I mean, stable is good for some things. Stable is bad for other things. Think of the ultimate stable system.
Doesn't move.
Right? You know, drop a particle to the bottom of a black hole. It ain't going nowhere. Right? I mean, it would never deviate. The very fact that you want to turn or change something is therefore something that is, as an action, pushing you out of your stable zone. You know, it may damp back down, but you are pushing that system. A really stable system doesn't want to change. You'll get rid of stuff really fast. As you start pumping the energy in, it tries to get rid of it so that it doesn't disturb it from its course. Now, if you like the course it's on, that's a wonderful behavior. We call that noise rejection and stuff. If you want it to turn, that's a bad behavior. Therefore, the ultimately stable car would never turn. Okay? So there's obviously some disadvantages. Aircraft designers, when they want a very responsive aircraft, or car designers, when they want a very responsive car, guess what they do?
Unstable.
They start making it unstable. Because a very unstable system is going to want to turn all on its own. Right? Even the slightest amount going that way will turn quickly. So there's a pressure to go this way, and there's a pressure to go that way. This is the trade-offs. Right? Any system worth designing, right, a non-trivial system, is going to have a trade-off. You can't get everything you want. So you'll have a region where you say, you know, this is my minimum response time to get behavior I want. You know, but I want it to get there and be done in a certain finite period of time, so it's got to be less than this, which will give you a region where you say, that's my ideal performance zone, and you've got to get everything into there. Make sense? So that's kind of our concern. Too stable, it's boring, right? Too unstable, it just blows up in our face. So you want to kind of be in a region. Good? All right. At least this blue color erases nicely. So we feel comfortable with first order systems and how they respond.
Yeah.
Are all of you familiar with this? How many people have actually seen this type of stuff? I just want to get, maybe about a third or so. All of you comfortable with the speed? Too fast, too slow? No? Good? Okay. Let's go up to a second order system. And through the magic of a whiteboard, and let's see. Now I'm going to rename these.
Imagine if I had to write my notes.
All right. By my very naming scheme, can anybody tell me what type of system I'm doing?
Force.
Mass spring damper. Right? Excited by some function. So this is kind of one of those Newtonian things where you have a little block. You can kind of imagine I got connected on the ceiling here, and I've got a spring, and I've got a little viscous damper that's going on, and there's a mass hanging off of it, and there's a neutral position, which is x, equals 0. And then I could either have something that's pushing that mass down, some electromagnet pulling it, or whatever I want that's going on. That's my force that's coming into it. All right? So I got something external that's acting on it, or I give you a crank and you can pull on whatever we want as it goes on. All right, but you have this, and this is K, and this is D, and there's mass M. Now realize the same exact thing would work with inductor, resistor, capacitor. You do all kinds of fun stuff as it goes. So I think we've already done the RLC circuits. So I'll use these letters. Realize same thing. Who cares?
Yeah.
Okay? But that's basically kind of the system behind it. So that means when I take, all I have added in is this, except I have to change my letters on here. But other than that, it's the same basic thing. Somebody help me out with what's in here?
SX squared.
Minus S initials of X. Initial of
All right.
The middle, is that that's a big,
That's a
big
D.
No, inside your first parenthetical thing, what you just wrote down.
Inside here?
Yeah.
The
Middle
middle
X.
term.
It's a big X. Middle X.
We're actually saying this is in time. Right? That's the initial conditions. But I don't know the initial conditions in S. I know the initial conditions in time.
Okay.
So I will both answer you, but also the idea is start to get the intuition behind it. And this is kind of that context thing so that you can look at it, and no matter how bad my handwriting is, you can still figure it out. Make sense? Okay, so the next line, this becomes K here, this becomes a D, and I've got S squared times M inside. I still have the X0 that comes across. Now I also have, and that's actually in X0 times D. And I've also got in M times S X0 plus a X0. We agree with that so far? All I've done is just taken these two and this one and brought them over to the other side. And then I've got the terms that have X sub S, and I've factored them out. Good? And then, of course, I'm going to divide by that. So, and I'll kind of regroup these. So I get MS0 plus X0. And I've put the ones that have S here and the constants out here. And then we have to divide S squared plus ds plus k. So far, so good? Now, this is still not done from our perspective. And the reason is, if you remember, on the other one, I had a leading term of 1. Can I get a leading term of 1 here in general? Absolutely. It's normalized. Divide top and bottom by m. It'll turn that into 1. That's a fancy multiplication by 1, isn't it? Now, so I could do it. Now the question is, do I want to do that?
Yeah.
Yes, I do. Why do I want to do it?
The
Yeah, it
transformation.
makes it A, easier to find the poles, but B, I've got to have some standardized way to find things in the table. Right? So if I normalize, if I don't normalize this, I have to write really ugly looking expressions where it's hard to find the powers and things of that sort. If I normalize by it, I can, in essence, have all of my tables start with S equal, or the highest power of S equal to 1. So it reduces the complexity of the table a little. And since we want to do things by lookup, it's a lot easier. It makes a lot more sense. So this is why I want to do this next step, is to make my life easy for later on down the line. So what I'm going to do is divide top and bottom by m. That's the multiply by 1 trick. So it doesn't change anything. I don't have to do anything on this side. I multiply by 1 here, I multiply by 1 here. But that gives me f of s over m plus s. This is why I didn't move that m. I'm going to put this in parentheses just so you notice it's a power of s there. Plus, and then I have d over m x0 plus x prime. That's the top when I divide through by m. And the bottom just becomes s squared plus d over m s plus k over m. If you notice, when you solved your physics equations and they ended up solving, you always ended up with k over m gives you the idea of your frequency that it's going to oscillate at. D over m gives you the shape of the curve in some sense. It relates into it. It's not perfectly by itself, but it's a big portion of what's going on. So you're getting the ideas of what these terms are really accomplishing, and it just allows us to standardize all the systems. Huh? So I make the same argument about this, right? Assume for a sec, as we talked about this is either going to add polynomials up here, or it's going to add exponentials. Exponentials just shift things, so who cares? Done with it. Let's consider it's just a polynomial. If it's a polynomial and it's higher than s in power, right? I can always, anything that's s squared or bigger, I can always get rid of by dividing. In which case I'll get a remainder up here that looks like s in that one. Right? And then I'll get some other terms that will just be a bias, adjusting where the asymptote's going to. So it's trivial to reduce it down to just saying something that looks like that. K1 times s plus K2 all over s squared plus, whatever's on the bottom, maybe I'll call it B1s plus B2. Do we agree I can, in essence, write everything that we're interested in into this form? From our earlier discussions on what could f of s be. If you know what this does, you know what the system does. Now, we want to ask a question about what's going on up here. This I can rewrite as K1 times s over s squared plus B1s plus B2 plus K2 over s squared plus B1s plus B2. Do we agree? I can get something that looks of this form. Everybody know what that is? Well,
Or a completed fraction.
think about inside of your terms here. Do you have anything that looks like this? In S and something that has a highest power S squared on the bottom in the tables that we have generated? I did this one on the board, so I know it should be in your notes if you have it. It'll look, yeah, cosine, right? Looks like this.
Yeah.
But you're missing the cross term, aren't you? That's a big problem, isn't it?
Well,
No, it's not really a big problem. You know why? Because you could just complete the square, couldn't you? To get that middle term and group it in here. So you'd have something that looks like this. You know, S plus some cross term squared. But then I could just go plus A over here. And just stick a minus A over here. And what do you have now? Well, S has been replaced by S plus A. That's a shift in your frequency space. We've already said a shift in frequency space causes
Delay.
a multiplication by e to the minus at in time. Shifting by A in frequency multiplies by e to the minus at in time. That's one of your properties that we developed. Okay? I think we actually wrote it this way: e to the minus at times f of t is equal to f of s minus a, or s plus a. It's one of the properties we developed like 2-3 days ago. I said, remember this one, I was only going to develop ones that were really important to us. Okay? And this is one I kind of had to backwards into a little bit that went on, you know, and I kind of picked it and everybody's like, oh, you know. And it really is, I know I want something of this form. This becomes important because it allows me to deal with this. Since we know that, you know, this is now of this form, right? S plus A for those. Well, that's the same as what would be this, except the result of its time domain has to be multiplied by e to the minus at, the shift amount. And this goes to cosine of omega t, and then the s being replaced by s minus a is going to cause this one to get multiplied by e to the minus at. So what is that? A damped cosine, isn't it?
Yeah.
That's telling you you've got e to the minus at, we've already talked about, gives you this lovely little curve. Cosine's going to flip about its axis, so we put the envelope on both sides. It starts up at 1, so it does this. Make sense? That's caused by this part. Right? Feel comfy with it? So when you look at that and you see the S term up there, essentially it's cosine. Good? Or marginal at least?
that was a bit fast.
What's that?
That was a bit fast for me, actually.
Okay.
Yeah, just the
So did it make sense? Right, we have this.
Mhm.
We've agreed this is what it is.
yeah.
Right? I can split this into two forms over here, right?
Yeah.
So that I can get, you know, my relative errors. And I just said, hey, look, you know, when I do this, you know, I pulled the K1 out just to go on. When we go on here, so I say, okay, this is K1 times here. So I technically add K1 times this. I added the A here,
Absolutely.
which means I have to subtract, technically, A times K1. So I just stick it over where the constants are. It's almost as if I knew in advance and I did this. Right?
Okay.
You know, there was no way I could have justified that earlier on. I had to get down to that area to justify why I wanted to do it.
Okay.
And then I had to go backwards. Oh, I could have done this. Right? Or I just had to magically pick it in advance and you're like, why did that work? Okay? So I'm trying to walk you through where you would figure it out on your own. Right? If you read the book or anybody else, they just kind of just give it to you. I always hated that. So I'm trying not to do things I hate. And so that's how I knew to do this. And the reason why is I got down and I looked at it and I had an S over something involved in S squared. And I want to use my tables, right? Because essentially I don't want to do the work of using that integral to go backwards. I'd rather look it up in the table. So if I can massage it into the form of the table, then I can use the table and do less work. So that was the entire motivation for doing this, right? So then we just noticed that it was something of an S over something that was S squared plus dot, 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 right? And we looked it up and we found out, oh, an S over S squared, cosine has that form, right? And cosine in particular looked like that. Then the question was, how can I massage it into that form? Well, I have cross terms in the middle. The only way I could do it is if this S looked like some S plus A, S plus A squared would give me a cross term. Right? And I could appropriately pick that A, right, so that 2A was equal to whatever the appropriate cross term piece is. Does that make sense?
Okay.
Which in our case is the B1. Good? So that's why we did this. We were just trying to say, hey, how can I utilize my table so I don't have to make up new stuff? I mean, because clearly, if you want to do every function in the universe, right, you'd have a pretty big table. So now I want to do a smaller table and be able to get nearby functions. So that's what the properties do. You have a couple of lookup ones, then you have properties that allow you to grab nearby results. So I don't have to store everything. Is that good? Okay. So that's why we did what we did. And so then at that point we said, okay, we've got this. And if this is S plus A down here, now we want to say, well, how do I get, I've got this on the bottom, I've got to call that in essence some type of an S. Right? Is there any property that lets me treat that just like normal S? And we go, oh, S plus A,
That's the shift.
that's this. And that just does shift, it just multiplies by an exponential. Right? And it's just the normal function as if this wasn't here, multiplied by an exponential. We go, oh, that's a cool property. That will let me treat this just like the bottom. But that means I've got to have S plus A up top, because every S must have S replaced by S plus A in order for this property to be true. So I had to put the plus A up here. Otherwise, I couldn't use that property, because if you just have it substituted down bottom,
Just gets small.
it's not the property. The property is every S replaced by S plus A. So I said, okay, well, in order to get a plus A up here, I got to do plus A minus A. I got to get rid of the minus A. Let me just stick it on the other term. And I just get K2 minus A times K1, but that's all just a number. I just get a new number, but what do you care what number it was? Right? So that's kind of the rationale behind it. Does it make sense? So all we're doing here, right, it's a very fancy thing to say complete the square. Right? Because that's all I did. I completed the square. And if you complete the square, the term basically this S here is generating is a cosine. Right? So this, with an S on top, is cosine. And that's the one we did in class, right? And then we also have a second one here, which is some constant over this. But that means I've got a constant over an S squared term on the bottom. What's that? Sine. Right? But sine right, looks like a squared plus omega squared, but I've got cross terms, so I complete the square to get rid of the cross term. Same exact trick. So now I end up with, there's no S up top, so I don't have to worry about substitution up top. So I end up with an S squared that's been shifted, plus omega squared and some constant on top. Right? No worries on that, yeah?
Would that only work if the constant up top is equal to omega then?
No, but thank you for asking. So technically speaking, I need, sine looks like this, omega over sine squared plus omega squared, all right? But what I have is k, some k, you know, whatever we want to call that k3 or something, right? But I can multiply by 1, can't I? We agree? And I can just pull k3 over omega out. Now I've got this times a constant.
It's just some factor of sine.
Which is, but this is, no, it's not even that. A constant, this is one of the properties I did improve because it's really pretty trivial. But if you have a times f of t, it Laplace transforms to a times f of s. This is trivial because it's an integral transform. Right? I mean, just literally stick this in, pull a out, and then notice that it's the Laplace transform of f, and you've got a times f of s. So it really is a very trivial one to prove. And this is because integrals are linear. So therefore, it's going to be linear. If you scale one, you scale the other. No worries. So because of that, once I pull that out, this is just a constant times it. So, you know, I'm not worried about, that's just the scale factor. How large does it start? Right? This in essence gives you the starting value. Right? And this gives you the shape and what's going on. So the fact that it's not equal to omega up top is no problem. It just adjusts what the scaling is. Fair enough? Everybody's really quiet. Coffee machine dead, too fast, too slow.
The guy downstairs was gone for line 15 for coffee.
You know, I mean, the real question is everybody okay? Does it make sense? 'Cause if I plow past this, the next couple things I'm going to do will make no darn sense if you don't get what's going on here.
Would it always be a sine, or could it also be two exponentials? Could be.
Yeah. So, but this is the fun part. If you think about it, you know, some constant times s plus some other constant. You're getting a cosine here and you're getting a sine here. So what you've got in both of them did this s plus a trick. So if you think about what's really happening here, I've got, when I come back over, e to the minus at times a cosine at that frequency, plus a sine at that frequency.
So it's an underdated.
With potentially some, you know, k3 over omega here, and I forgot whatever the constant was on the other one, right? But some other constant k4 out here, which are the initial conditions that they go on. So it looks like a sum of sines and cosines, right? Times this. Well, if you take sines and cosines together, it just looks like a phase-shifted trig function, right? It's the other way you can do it. I could combine these two together as a single phase-shifted trig function. So I've got one, in essence, cosine starts high with this envelope, and sine starts at 0 with the envelope, and does the same thing, just, you know, a little bit out of phase. And then, therefore, when you're adding them together, the net of these two will be a shifted trig function, which is why, in reality, you're going to get something that looks, you know, starts somewhere in the middle and goes. If it starts right at 0, it was just sine. If it starts right at the initial condition, then it was just cosine. Right? If it's somewhere in between, it's a phase-shifted version of them, or a summation of the two. Yeah.
So going back to the example we were working at before, that's just going to generate an e to the k over m or d over m? I'm trying to figure out what would my
if you think about what's happening here, what we discovered was, in order to handle this, right, because B1 is this, right,
Yeah.
that's our cross term, we know that this right here has to generate sine and cosine.
Yeah.
And the only way to intelligently write that is to kind of group these together as if it was a completed square. Does that make sense?
Yeah.
So if you want to think about it in this way, right, let's take that original bottom, which is s squared plus d over m times s plus k over m. If I want to complete the square on this, how do I do that? Well, I assume that this is, you know, equal to the middle. If you took, you know, whatever S plus A quantity squared, that's just S squared plus 2AS plus A squared, right? And then I have some other external thing out here, you know, pick a variable I don't have B up in this particular spot, right? So then I have, you know, plus whatever the B is.
Yeah.
So this A squared plus B has to be Km, and 2A has to be D over M for this to work. Right? In order to get into this form. Okay?
Yes.
Right? That's what we mean by completing the square. I just write it as if it was a completed square, multiply it out, and associate terms. It's got to be where they came from. Right? So, you know, to get what A is, well, 2A has to equal D over M. I want to know what A is, so I just divide both sides by 2. There you go. That's your shift.
So we're going to have e to the negative d over m, 2m dt, and then a
So
cosine. And then
that's
we figure
A, and we've said that what you get is e to the minus AT. So, and A is equal to D over 2M. Oh, there you go.
Yeah.
That's that part of it.
So now we just need to figure out omega.
Right? So that's telling you the damping. I told you D over M gives you something about the envelope. I said, but it was slightly modified. Dividing by 2 is a slight modification, in my opinion.
Yeah.
Okay? So this gives you the shape of the envelope. Right? And that's dependent on the damping. Oh, I deleted my thing. It's based on the damping. How much energy are you losing by rearranging the molecules in the, you know, dash pot, or, you know, if it's moving through air, the air being, you know, redistributed, so on. The non-conservative force. Because that's what dash pots are, right? The dampers, they're all non-conservative forces. Because all your energy is non-recoverable, you just rearranged all the atoms inside the box. And it took energy to rearrange them, but rearranging them back doesn't give you the energy back out. Right, so that's why it's called a non-conservative force.
Yes.
Am I saying things that are familiar to people when they took physics?
Yes.
Right? I'm trying to make you understand where they are, so when you think about them, you go, oh, right? This envelope damping off is just giving me what's happened when I'm rearranging all these molecules. Non-recoverable, therefore it's going away. What's left, then, once I've done that, is the omega squared. Well, that's the, you know, let me just write this as kind of a combined function. You know, we can say it's cosine omega t plus some phi, some phase shift. Right, that covers both the sine and the cosine. So the omega, this is the crucial part, what's the oscillating frequency? Because the phase shift just says when does it start. Okay? The frequency tells you how fast it's oscillating. So the omega that's on here, that's completely determined right from there. So for us, the omega, right, technically speaking, omega squared is B. Right? So for us, B equals omega squared. But B, I have to get from the equation A squared plus B is equal to K over M. Do we agree? B itself is therefore equal to K over M minus A squared. And A squared is D squared over 4 M squared. Right? So there's B. That's omega squared. So I take the square root to get omega. Okay? Now, we could simplify this up. There's other ways to get at this. I just want you to see I can kind of hammer this out directly from what's in here. I can then take from my direct components and figure out what's the oscillating frequency with the dash pot in it. Right? Like I said, there's cleaner ways of writing it. It'll depend on whether this is positive or negative, all kinds of fun stuff.
Well, it's just a
But
number,
we can,
though, right?
Yeah. Right now, this is just telling me, that's telling me what is the omega as it goes in. And you can calculate that in the way you do it. Fair? So in general, I can get it. That means basically what we're considering, right? The top only is really adjusting what my phase shift is and the magnitude. So that's fairly trivial stuff. That doesn't determine really the shape of what's going on. So we're basically going to become concerned not as much with the top, again, the bottom that goes on. And now I don't need to worry about d over m and k over m. I'm just worried about s squared plus something times s plus something. That shape will always generate this type of behavior pattern. Okay? And we can see what's happening in the time domain. It just looks like something like this, right? Which graphically looks like this, right? Exponential damping in, away we go. As long as I've made an assumption by drawing that. What assumption did I make? Right? This kind of damping in, the envelope decaying, makes an assumption about the envelope, doesn't it? What assumption does it make? That d over 2m is positive. Right? Is that going to be true for one of these kind of mass spring damper systems?
Yeah.
Well, if it's not, either mass or d would have to be negative, right? How many of you have measured a negative mass? Okay, you know, it's
Somehow.
so that ain't happening. How about d is negative? If d is negative, think about that. That's like you stick, you know, a damper, all they do is they stick some viscous liquid and they put kind of like a paddle in it. So as it moves, it has to rearrange the fluid, the viscous substance it's moving through. So this would be like sticking something in a viscous fluid. If D is negative, it starts pushing you. Okay? It moves you on its own.
That's mildly concerned.
Like
Yeah. Right? You ever encounter that one happening?
the movie Flubber.
You know? Now, so this is an easy way to prove that flubber is stupid. Okay? Because watch this simple thing. If D was negative,
Getting energy for free.
you get energy for free, which is perpetual motion. Woohoo! Okay? So you can prove the very premise of that thing is just a dumb idea.
Still fun.
Hey, this is why I don't go to yeah, nobody takes me to movies. They're like, the first thing I go, that's dumb, that's a perpetual motion machine. And then, you know, I get ready for 3 blocks, goes, dork. You know? And I smile happily thinking maybe I've educated them. You know? But more likely making them just think that dorks are annoying at movies. So but realistically, that for a practical system is not going to be it. You would need active components in order to do this. For passive components, spring mass systems, this is guaranteed to be positive, which means it's guaranteed to damp.
And the same for passive.
You have to have something that can supply energy into it, which means I need a motor or something else where I can be pumping energy from some external source.
And that's the same for passive electronic circuits too, right? 'Cause you're always gonna
That's why they always damp. You know, I mean, think of it, if you had a negative value of resistance, right?
shoot more.
You just start a little current flowing and damn it, it just gets getting bigger and bigger. You know, I could run the universe off that. Okay? I mean,
Be a neat resistor.
it'd be pretty nifty, but, you know, it just doesn't happen. So, you know, you could walk through whatever ones you want on them. It makes no sense. So, you know, clearly this is going to be for passive components. Is it theoretically possible to get something that does become marginally stable?
Yeah. Add active components.
When you
Yeah, put active components.
Add it up.
Could it become unstable?
Yes.
Active components. But remember, those active components are going to draw more and more power. Eventually, what really happens on those is it draws too much power, and it either blows a fuse itself, it breaks itself, or it damages the power source that was supplying to it. This is why we're concerned about it. Right? Make sense? Well, besides that, I mean, it's unbounded itself. But ultimately, your electronics will break before it goes unbounded. So that, I mean, in real systems, that's what they're concerned on. So like if you're controlling a factory or something like that, and this is something computer engineers do, they build a control to Mott's or the factory, if you let it go unbounded, you are revving their engines up way too fast. Can anybody think of a practical case where this has been done deliberately?
That's a virus that was done in
That was the virus that was done to take out the Iranian
centrifuge. Yes.
yeah, the centrifuges to stop them processing, ore. So they sent in a virus that caused them to spin up the motors too fast. It made it mildly unstable as it went. It spun too fast and ruined everything. It wore out the bearings on their stuff, and all kind of their systems failed. They processed incorrectly, and they got garbage out of what they put in.
At a mild
Right.
and stable, though, when you're spinning that fast, mild quickly becomes massive.
Yeah, so I mean, that's the whole point. That was the whole purpose of that thing, is somebody just went, what if we made them unstable? Ends that problem, right? And away we go. So, there's other cases, but imagine if you did that accidentally on your own plant. Right? They're not going to be very happy with you. So these are things we deal with. Does it make sense? So when you see things that look like this, second order systems, think damped sinusoids. What would happen if there was no damping?
You would have no phase.
Okay? Well, isn't that awesome in some sense? Think about what you've got there. You've got S squared plus K over M. Right? If there's no damping, if D equals 0, S squared plus K over M, that means K over M is my frequency squared. So this is where you get the physics result, because they always give you no damping. What they get is that omega squared equals K over M. And then you take the square root, and you get that. And that's physics 221 when they get to these systems. Right? They always give you that result. That's the undamped one. You can now see exactly what happens when I add damping. I get a minor perturbation of that. It just changes slightly. Right? So if D equals 0, this one reduces to the result of the simple undamped system. When D is positive, it moves away from it and it changes the frequency. So as you add damping, your frequency changes. We call that the damped frequency. So this is something we're going to want to see. Can we see that inside of our S-plane, all of this information? So does it make sense what we're looking for to understand what's happening? Because if I can tell you what the damped frequency is, that tells you the oscillation. If I could tell you that from an undamped system, that's even kind of nicer, right? You tell me the undamped system, and I tell you exactly how it ends up being damped. That's a good addition that goes on to it. And if we could just see that by looking at the S-plane without having to invert it, it's even better still, right? So you know what the answer is going to look like before you do it. We all clear on what it will look like in time and what we want to see. Okay?
Yes.
Let's just see it real quick then. What's going on inside the S-plane? I need more board. I'm going to erase this. I trust you all have it in your notes. If not, it's probably available in about 1 billion places online. So we said what we're really concerned with is something that looks like this. S squared plus some constant times S plus some constant. Right? So maybe I'll just stick in whatever, K1, K2, or whatever we want to call it. I want something that looks like this, right? Now, we've already identified that this should look like its fundamental frequency squared. So this is either going to be called by people, they either just call it omega, or they call it omega 0, or they call it omega n. It all basically will mean the same thing. I tend not to like omega by itself, because we also use omega for the frequency that you're driving it at. So if you pick omega here, yes, you save yourself one letter, but it's confusing later on when you ask, what is the omega of S? Now you've got omega in 2 places. So I would suggest you either use 0 or n. 0 means the fundamental. Remember, there's harmonics. So omega 0 is that first fundamental harmonic. Omega n means the natural frequency. Right? So that's the undamped one. What would it be if you were in a vacuum? And naturally, everything's in a vacuum. So I find it funny, but yeah, it is called natural if there's no air around it. So that's omega n, but we said it's squared. So instead of calling that K2, we're going to call it omega n squared. Now, when we're taking a look at the squares that go on here, we really want 2 times something here, because that's easy to complete the square. Okay? And ideally, it would be nice if this was related to Wn, but it's not perfectly, so we get zeta times omega n, which I cannot really draw a zeta to save my life. So what you get is the famous squiggle.
Yes.
Okay? So, every place I've ever been, evidently none of us know how to draw this darn letter to save our life, which is proving I'm not Greek. But I think it's supposed to technically look like this or something, but I can't draw that, so it becomes that. So imagine that was a zeta. My apologies to Greeks everywhere.
Why on earth did they pick zeta to represent the damping factor?
Well, think, we always use Greek letters for scalars.
Yeah.
That's a standard concept. What do you have left? Right? I mean, we've already used theta and phi. Pi is taken up. You start walking down all of them. There's not an awful lot of them left.
Yeah.
So, they
So
don't have
it's
some
good.
other connotation to you. Rho means density to an engineer. Okay? So as you start going through these, a lot of these are constants. So we picked the one that nobody could write, therefore we're pretty safe. So, so we picked that, and we call this the damping factor. Because remember, this middle term is damping, so this gives me a damping factor as it goes. Now, another way, anybody know a shortcut to complete the square?
I don't remember it, but I know there is one.
There's a really easy, neat thing that already did the completing the square for you. That's the whole thing of the quadratic formula. That's how the quadratic formula was generated. They completed the square and then solved for the pole. Really what we care about is, where is the pole? Because you see a variable on the bottom. So what should you be concerned with? The denominator could go to 0, couldn't it? There, somewhere out there is a choice of s, 2 of them actually, that make this denominator go to 0, which makes this whole thing blow up. So if you know where that happens, you have characteristics to describe what's going on over here. They're equivalent. So all I have to do is find out where the bottom goes to 0, stick that in the plane, exactly analogous to the first order system, and I will be able to tell you everything you wanted to know about what's happening here. Okay? So that's my concern. So I want to know where the poles of this are. Before we did it by completing the square with the justification of, I want to be able to find the inverse transforms. Now I'm saying I don't even want to bother with that. I just want to know what the properties are here. I already know what the inverse transform looks like. So if I can look at the basic properties here, I can make the decisions, and then just let the computer calculate that inverse transform for me. Right? But I want to make sure that the properties are satisfied here. If I can satisfy those properties here, right, whatever I want to happen in time domain, I can do less work. I just let the system do it, and I know it's going to be right because I already solved it correctly. Make sense? Okay. That's kind of the goal. We just want to be able to figure out the properties without having to inverse transform it. And then just automate the rest of it. So we make these choices as it goes. Therefore, we're looking for when this bottom equals 0. All right? That will also cause it to grow unbounded, so we again call them poles. That happens when we can write this, s squared plus 2 zeta omega n s plus omega n squared equals 0. This is akin to factoring it, so we get, s plus something, right? Whatever, Fred times s plus Wilma. I can rewrite this factor. That's the whole point of that quadratic formula, right? You can tell me what the poles are. So, when s is equal to Fred, this thing goes to 0. So that's one of the two. Huh?
Minus.
Or minus Fred. So when I get s equals minus Fred, which is equal to one of my poles that go on here. Same thing over here. Good? So if I can find those poles, which is just stick that in the quadratic formula, I know everything that I need to know to move it. Does that make sense? Okay. Awesome. So that's kind of the goal. This is just motivation for why do I do it. All right, anybody remember what the quadratic formula looks like?
Yes, negative b.
Negative b plus or minus square root b squared minus 4ac divided by 2a. Wait, b squared
B
minus
squared
4.
minus 4ac. I dropped a term.
Divided by 2a.
All right, so these are where my poles are, pole 1 and 2. All right, pole 1 is the plus, pole 2 is the minus. Fair enough? Now we just substitute in. So I get minus 2 zeta omega n, right, plus or minus square root of 4 zeta squared omega n squared minus 4 a times c, which is omega n quantity squared, all over 2a. All right? So I first note that everything on top and everything on bottom is multiplied by 2. Right? So I've got 2 inside the square root is 4, so that's a 2. Because if I pulled, these both have 4s. If I pull the 4s out through the square root, it's the same as having a 2 there. But then I got 2, 2, 2. I can dump the 2s. You agree? I got an omega n squared on both of these. Right? So I got an omega n on both of these, or omega n squared. I can pull the omega n squared out. When it goes to the square root, I get a omega n. So I get this little zeta squared minus 1. Make sense? Okay. Now, we got to ask ourselves some interesting questions about this. This describes where the poles are. What happens when zeta squared is bigger than 1?
It's positive. It's real.
This is positive inside, so it's real, which means it's all
On a real
in the S-plane. I think it's less chunk on the board over here. It's all on the real axis. Why am I sticking in the left-hand plane? Because that's the stable plane. Right? If it goes over on this side, active components going unstable. So the same thing we developed before, it's still stable, marginally stable, or sorry, unstable, marginally stable, stable. Right? So I'm going to draw my stuff in the stable plane because that's where you want to end up. If any of these things ever end up over here, it's unstable, you better get them back over. So if this is or zeta squared is bigger than 1, this is positive, this is real, it's a real plus or minus a real, you've got 2 different poles right on the axis. Right? Now, that's telling you something about what's going on, because we could actually take this same thing and we could correspond them to the damping coefficients and everything. It goes on, but this tells me now, these ones go on here, we actually consider the response of this. Right? If this is bigger than 1, it means it's a large value, right?
And it's overdamped.
Right? And so, yeah, this is what we call overdamped. That means this is big. Right? Your frequency is whatever your natural frequency of the system is. So I'm just saying right now, what if I kept increasing this? Make it bigger and bigger and bigger, more and more positive. That corresponds to making your damper D bigger and bigger and bigger as it goes on, which means it's going to damp out really fast. That's why we call it overdamped. Okay? Really big values of this, it just goes shloop, right? It's like trying to pull something through molasses. Right? It's going to move really, really slowly. Right? So, you know, and the more viscous you make it, the thicker, the slower it's going to go, that's bigger D. So, as this increases, it's more and more critically damped. Well, both of these are on the real axis. Do you know what the response of these poles are? You just figured that out already from the first one, first order systems. Didn't a first order system generate a pole that looked like this?
Yeah.
You got two of them. How fast does this one damp away relative to this?
Slower.
This is the slow going away one. This is the fast going away one.
The fast one swamps it. Where?
The slow one swamps.
Okay.
Right? Technically speaking, and this is going on, right? I've got one that disappears really quickly.
Okay.
Right? So it really only will appear, this one only really appears in the very beginning part, and then it's so close to zero it in essence does nothing. Right? So what you get from these two is this one has, as it's going away, here's your time response. This one's dropping really fast, and this one is also dropping, but it's dropping slower. Right? So only for this little period does it make a bit of difference, but this one's carried on for a long time. So when you add these two together, right, you get this one on top, which kind of gives you it even looks like it's a steeper drop-off, doesn't it? Is there any oscillation?
No.
Right? You put too much damping in, your system stops oscillating. It's just right, you put anything, even if you're trying to oscillate on the thing, it can't respond fast enough. Pull it through it, it just slowly sloops through. You get this really, really, over-damped response. Right? If you put a really fast vibration on something that's, in too viscous a liquid, too much mass, it's just not going to move. Right? If you reach a certain point, it just stops. There's some areas where they'll actually respond, some areas they just stop. Think about your washing machine, right? Sometimes it gets to a point where it's kind of a little bit off-center, it starts vibrating. If you go faster and faster as it goes on, it'll actually smooth out. Same thing on your car. Driving down a bumpy road, right? You drive faster, what happens? It smooths out. You blow your shocks, but it smooths out, okay? So you get a smoother ride as it happens. Right? The system can't respond fast enough, so it just doesn't. Right? It's just completely removed it. It's damped it away. And the one that's getting rid of that is your shocks as you're going down the road. So that's exactly what you would expect. Right? We've got experience that says that. So when they're both real, it just acts like two first-order systems summed up. What happens when zeta squared becomes 1? Right? If zeta squared becomes 1, zeta is 1. Right? As far as we're concerned. So what you get is this becomes 0. That's 1. It just goes to omega n. But they're both. Right? So now what happens is as zeta gets closer and closer to 1, these two poles start moving together, don't they? Mm-hmm. And when zeta equals 1, they meet. So if you want to think about it, if you take zeta omega n, that's this kind of middle location. Zeta omega n. That's this midpoint. Right? I mean, technically minus zeta omega n because I'm in the left half plane. But this is therefore the distance the two poles are away from zeta omega n. So this distance here and this distance are the same, and they are just omega n times the square root of zeta squared minus 1. Right? One goes that way, one goes the other because it's plus and minus. As this goes to 0, they start coming together until they hit and they overlap. At that instant, I still just have, we usually put a square up there just to let you know there's two of them on top of each other. Some people draw this kind of funky double X. You'll see that sometimes too, to tell you there's two there. I think that looks like there's another one nearby. So I personally hate that, but you will see it sometimes. I think the squared makes more sense because then if you have 3, I just put 3. Right? So, but if I had two of them right there, right on top of each other, what do they look like?
It looks like a single order system.
It looks like two first order systems that are exactly the same, which means neither one is disappearing faster. So they respond exactly the same, just kind of twice as big. So it just, They're exactly the same, so, you know, it's just twice the value. So that's right at the edge. There's still no oscillation, is there?
Critically damped.
That's what we call critically damped. They've now moved together and they've hit. And the question happens, what happens when zeta squared becomes less than 1?
Move to the complex.
Yes, they've now moved together, they've hit, and they bounce off into the complex plane. Because what's going to happen when this becomes smaller than that, I can just reverse the order and pull a negative out. This is just -1 minus zeta squared, right? And this is now positive. And I just pull the -1 out. It's called J. Right? We call it J because I'm an engineer, and engineers don't use I. I is current. So J is square root of -1 to me. Right? So all I've got is this is now completely normal. It's a real number again. And so this, if you look at it, relates back over to our damped frequency that's going on. And this is now, again, still the same center. They've now just gone off. And it's plus or minus J, so they move off in pairs. All right, what we call complex conjugate pairs. They're centered right above, that's the real part, which is still giving me that kind of damped area. And this is now telling me what the effective damped frequency is. Because now I've got these two. They're not on the real axis anymore. That corresponds to this response right here. This is the first time it does. And if you look at it, this one right here is 2 zeta omega n. Remember when we completed the square? We picked 2 times whatever our damping value was. That was our A. 2 times A, we completed the square. So zeta omega n was the part that goes in e to the minus zeta omega n t. That's your envelope. That's telling you how much the damping was. Because before we called it A, we just put 2A. But A is zeta omega n, so you can replace them universally. All right? So that's my damping. So how far over to the left you are tells you how damped you are, even when you split off. It just gives you the envelope. And then how far up or down you are is your frequency, how you're oscillating. Right? If I'm purely oscillating, but there's absolutely no damping at all, I'm right on the border here. Because e to the minus zeta omega n, if that's 0, that goes away, I just get sines and cosines. So your sines and cosines look like poles right on your axis. Right? Just the imaginary axis. So this gives you exponentials, this gives you sines and cosines. Combinations gives you exponential times sines and cosines. Shouldn't be too surprising. That's why we want to develop why were sines and cosines written as complex exponentials. Then you just realize, oh, the whole thing is just describing exponentials. Fair enough? Okay, I notice I'm over time. So I'd like to finish up a little bit just to let you see how the frequencies change a little more next time. And then we'll move on to the next thing. The goal of this, just to kind of get in your mind, why did we do all this stuff? I want you to be able to look at the S-plane and say, what's happening? Because that's where we're going to do all of our analysis. And you need to know what's happening and what needs to happen to make it behave the way you want it to behave. Because at that point, if you know what to do, you can now pick a control that will help you to achieve that purpose. Right? If you have to constantly convert back to time and then figure out, oh, what'd that do? It's going to take you forever as an iterative process. You know, convert to time, see what happened. Change it a little, convert to time, see what happened. It's impractical. If we can see what happens right in here, we can manipulate things here, which is very easy, it's very efficient, and then we know exactly what's going to happen on the other side. So once we get it to the place we know it's going to work, you can just hand it down the line to somebody to implement that in code. Easy peasy, right? That could even just be MATLAB or LabVIEW. Just say this is where I've moved it to and let it make code for you. They will automatically generate compilable code for your controllers. So away you go. Make sense? Awesome.